Good morning, everyone, and thank you for joining us today. I'm Ravi Babu Dammu, Senior Engineer at Enritsu India Private Limited, and I'm delighted to welcome you to this special webinar on passive device characterization with vector network analyzers. This session is a part of Enritsu's 130th anniversary celebrations, a proud milestone that reflects our long-standing commitment to innovation in test and measurement solutions. Today, we will explore how modern VNAs, especially those are operating up to 110 GHz, are essential tools for accurately characterizing passive components such as filters, couplers, antennas, and cables. We will look at both coaxial and waveguide based setups and discuss how to choose the right configuration based on your application. Whether you are working in R&D, production, or advanced millimeter wave systems or design. We will also touch on key features like time domain analysis, calibration techniques, and how to interpret S parameters for real-world performance insights. Let's get started by understanding the fundamentals of passive device behavior and how VNAs help us unlock their true performance. Let's begin with a quick overview of today's agenda. This session is structured into 4 key sections to give you a comprehensive understanding of passive device characterization using vector network analyzers. We will start with the fundamentals, where we will differentiate between active and passive devices and introduce the concept of S parameters, which are essential for understanding how RF signals behave in a network. Next, we will dive into the vector network analyzer itself. We will look at this architecture, how it functions, and the importance of the calibration to ensure accurate and repeatable measurements. In the application section, we will explore the real-world use cases, specifically how VNAs are used to characterize antennas and filters, and we will touch on some advanced measurement techniques that go beyond basic S parameter analysis. Finally, we will wrap up with Enritsu solutions, where we will introduce our VNA portfolio and share some practical troubleshooting tips to help you get the most out of your measurements. This structure will help us build from the basic to more advanced topics, ensuring everyone walks away with actionable insights. Let's get started with the fundamentals of passive and active devices. This slide lays the foundation for our discussion by distinguishing between two fundamental types of components in RF and microwave systems, which are active and passive devices. Let's start with passive devices. These components do not generate any energy. They only consume it. The key term here is loss. Passive devices typically introduce attenuations into the signal path. Examples will include filters, cables, connectors, adapters, and mixers. All these devices are essential for routing, combining, or condition signals without amplification. On the other hand, the active devices, which will require an external power source, usually a DC bias, to operate it. Their defining characteristics is gain. That means they can amplify the signals. Common examples are amplifiers, active filters, and frequency converters. These are used when signal strength needs to be increased or modified. Understanding these distinctions between active and passive is crucial because the measurement techniques and performance parameters we use, especially with vector network analyzer, differ significantly between active and passive components. For instance, passive devices are typically characterized by parameters like insertion loss, return loss, while active devices requires additional considerations like gain compressions and noise figure. This foundational knowledge will help us better understand how VNAs are used to characterize these devices in the upcoming sections. Now we will discuss little about the device characterization. This slide introduces to the core concept of device characterization, which is essentially about understanding how a passive devices behave under RF signal conditions. We characterize a device when we want to verify that its measured performance aligns with its design expectations, relevant industry standards, or specific application measurements. This is especially important in high frequency systems where even small mismatch can lead to the significant performance degradation. Passive devices like filters, antennas, cables, and duplexers don't amplify signals, but they do affect how signals are reflected, transmitted, and are observed. These behaviors are quantified using key performance metrics such as return loss, insertion loss, isolation, bandwidth. Where the return loss means how much signal is reflecting back, and insertion loss is how much signal is lost in transmission, and how isolations, how the well ports are separated, and bandwidth, the frequency range over which the device performance is expected. The image in this slide shows a typical VNA setup measuring the S11 parameter, which represents input reflection. This is one of the most common measurements in passive device testings today. So for the know the device characterization, there are some key parameters which are available, which we need to do. This slide will introduce those type of things to you. This slide introduce three foundational parameters sets is used in electrical network analysis, which is Z parameters, Y parameters, and H parameters. Let's start with the Z parameters or impedance parameters. These relate voltage to currents at the ports. They are intuitive and useful for low frequency circuit analysis, but they require open circuit conditions which are difficult to achieve at high frequencies due to radiation and instability. If you will come to the Y parameters or admittance parameters, which relates to current to voltages, these are the dual of Z parameters and also used in low frequency analysis. However, they require short circuit conditions, which again are impractical at microwave frequencies. Then the third one is H parameters or hybrid parameters we called, which mix voltage and current relations. These are especially useful in transistor modeling at low frequencies. For example, H11 represents input impedance and H21 represents forward current gain. But again, they are not suitable for high frequency passive device testing. The key takeaway here is that while these parameters are available in certain contexts, they are not ideal for RF and microwave applications. That's why we rely on S parameters, which we will explore in this slide. These are easier to measure and more practical for high frequency characterizations using VNA. Unlike Z on Y or H parameters, which relates to voltage and current, S parameters describe how RF energy is reflected and transmitted through a multi-port network. They are especially useful at high frequencies because they deal directly with traveling waves, the incident and reflected power waves, which is exactly what a vector network analyzer can measure. For a two-port device, we typically focus on four key S parameters, which is S11, S21, and S12, and S22. These parameters are critical for characterizing passive devices like filters and antennas. For example, A good filter will have low S11, which is minimal reflection, and high S21, which is maximum transmission that we require in the passband. One important point to note is that VNA directly measure only S parameters. If needed, software can convert into Y, Z, H parameters. This foundational understanding of S parameters sets the stage for exploring how VNAs are architected to perform these measurements, which we will cover next. S parameters or scattering parameters describe how RF energy is reflected and transmitted through a multiport device. They are defined as the ratio of incident and scattered power waves at each port, making them ideal for high frequency applications where voltage and current are difficult to measure directly. We will break down the key terms here. Previously, what we explained about S11, S21, S12, and S22, where S11 represents the input reflection coefficient. That means how much of the signal is reflected back from the port 1. S21, which is forward transmission coefficient. That means how much signal travels from port 1 to port 2. S12, reverse transmission, which is how much signal travels from port 2 to port 1. And S22, reflection, output reflection coefficient, indicate how much signal is reflected back from port 2. What makes S parameters so practical is that vector network analyzers are specifically designed to measure them directly, capturing both magnitude and phase. This is why S parameters have become the industry standard for characterizing RF components like filters, antennas, cables, and couplers. Understanding these parameters is essential for interpreting VNA measurements and ensuring your device meets performance expectations. Now, we will discuss about the VNA architecture. A VNA will consist of three distinct main functional blocks. One is frequency source, which is used for generating a signal. And second one is the microwave test set, where it will contains of directional couplers or bridges, which is used to split the signals. And the last one is the network analyzer, which we will call the brain of the systems. Like it will includes both analog and digital processing components that make the measured signals and compute the S parameters. As you are seeing in the diagram, it shows how these blocks are interconnected to one along with along. Like you can see the source which is going to the DUT, and it will send the signals to the reference receivers R1 and R2, and the measurement receivers A and B will capture the signals, and after interaction with the DUT, and then a local oscillator provides the necessary mixing signals for down conversion and phase detection. Understanding this architecture is crucial because it helps us appreciate how VNA achieves such high accuracy and dynamic range in measuring both magnitude and phase. Let's discuss deeply about these blocks in the coming slide. The frequency source, where it all begins. The VNA generates an RF known signal, typically a sine wave, which is then fed into the DUT, which is device under DUT test. This signal acts as the stimulus for the measurement. And we will come into the microwave test set, which will do several critical tasks, like it will route the RF signal into the DUT. It uses directional couplers or bridges to separate the incident and reflected signals. These signals are then directed to receivers that measures both magnitude and phase. This setup allows that VNA to simultaneously measure all four S parameters like S11, S21, S12, and S22, providing a complete picture of how the DUT behaves. The last one, the network analyzer, is the processing unit. It includes both analog and digital hardware that takes the raw signal and converts it into meaningful results like VSWR as parametric metrics. This is where the data is calibrated, corrected, and displayed for analysis. Understanding this flow is essential for interpreting VNA measurements and for troubleshooting any anomalies in your test setup. Now we are giving the introductions to the vector network analyzer. VNA is which is the core instrument used in RF and microwave testing. A VNA is a precision measurement tool that captures the both magnitude and phase of RF signal. This dual capability of measuring magnitude and phase is apart from scalar instrument, which measures only magnitude. The ability to measure phase is critical for understanding how signals behave in complex networks, especially at high frequencies. We will discuss about the key capabilities of VNA. S parameters measurement, this is the primary function, measuring how signals are reflected and transmitting through a device. Frequency domain analysis, VNAs operate across a wide frequency range, allowing us to analyze how devices perform over the entire operating band. The time domain analysis, by applying inverse Fourier transformers, VNAs can also provide insights into signal behavior over time, useful for identifying discontinuities or faults. And the antenna testing, very widely used to measure return loss, VSWR, and impedance of antennas. This slide also highlights important terminology, vector versus scalar. Vector instrument will provide phase information, enabling complete characterization and higher accuracy, where passive versus active, VNS can test both through the setup and interpretation differ, and transmission versus reflection. These are the two fundamental behaviors we measure using S parameters. The images on the slide show examples of Enritsu VNA hardware, giving you a sense of what these instruments look like and how they are used in practice. These fundamentals will help you appreciate the power and versatility of VNAs as we move into specific application and measurement techniques in the coming slides. This slide reinforces the role of network analyzer, specifically a vector network analyzer, in characterizing electrical networks. Traditionally, network analyzers were used to measure various network parameters, but in modern RF and microwave applications, they are primarily used to measure S parameters. This is because reflection and transmission characteristics are most relevant and easiest to measure at high frequencies. Now, in some cases, measuring just the magnitude of signal is sufficient. For example, when you are checking an amplifier gain, you may only need to know how much the signal is amplified. When you are verifying the filter stop band rejection, you mainly concerned with how much unwanted signal is attenuated. However, for complete and accurate characterization, especially in linear networks, we need both magnitude and phase. This is where the VNA will shine. Measuring phase allows us to perform accurate circuit simulations, designing efficient matching networks, and carrying out time domain analysis, such as identifying discontinuities or impedance mismatches. So, while scalar measurements have their place, vector measurements, which include phase, are essential for high precision RF design and troubleshooting. This is why VNS are indispensable tools in both research and development and production environments. Now, we will discuss about the calibration part. The slide explains one of the most critical steps in ensuring accurate VNA measurements, calibration. Calibration is the process of removing systematic errors from your measurement setup. It starts by measuring a known reference device, comparing the measured value to the expected ones, and then generating an error correction table. This error data is then subtracted from all subsequent measurements to improve accuracy. Let's walk through the different calibration methods shown here. The first one is uncorrected. This is the simplest approach. Just connect the DUT and measure. It's convenient but not accurate, as it does not remove any errors. Where response calibration, basic method that corrects for frequency response. It is easy to perform and useful when high accuracy is not required. Coming to the one-port calibration, this method used for reflection measurements, which involves using open, short, load, standards. It removes error like directivity, source match, and reflection tracking. For two-port calibration, this is the most accurate method. It removes a wide range of errors, including source and load match, transmission tracking, and crosstalk. It's ideal for precise S-parameter measurements. Choosing the right calibration method depends on your application, required accuracy, and available standards. But in all cases, calibration is essential for trustworthy and repeatable measurements. Before we perform any calibration on a vector network analyzer, it is essential to consider a few practical but critical factors that can significantly affect measurement accuracy. First, always confirm the frequency range of your measurement. This ensures that your calibration kit, cables, and adapters are all rated to operate effectively over the desired band. Using components outside their specified range can introduce significant errors. Next, evaluate the condition and suitability of your cables. Even high quality cables can degrade over time or due to improper handling. Pay attention to the effect of bending the cables. Even a small gentle bend can alter their electrical characteristics. The impact of moving cables during after calibration, which can shift the reference plane and invalidate your results. Whether the cables can comfortably reach the DOT without excessive bending or strain. A best practice is to perform the calibration with the cables positioned exactly as they will be during the actual measurements. This minimizes any variation between the calibration and test conditions, ensuring the most accurate results. These all conditions may seem simple, but they are often overlooked and can be the difference between a reliable measurement and a misleading one. So always take a moment to access all your setup before hitting that calibrate button. Now we will highlight the versatility and importance of vector network analyzers in modern RF and microwave testing environments. Let's start with the type of measurements VNA can measure beyond the standard S parameters, which cover transmission and reflection characteristics. VNAs are also used for gain compression testing, which will replace some traditional power meters. Intermodulation distortion, which will replace a spectrum analyzer and a setup of two signal generators, splitters, long cables, those type of things we can avoid by using VNA. And the noise figure measurements and time domain analysis, which includes distance to fault testing, impedance profiling, and even eye diagram analysis also. This makes the VNA multifunctional instrument capable of replacing several standalone tools in lab or production setup. On the hardware side, VNAs are compatible with a wide range of device configuration for coaxial connectors, which are the most common to waveguide interfaces, single-ended or differential inputs, connectorless setups with fixtures using microstrip or stripline fixtures, and even on wafer probing for semiconductor testing, as well as optoelectronic device characterization. The diagram in the bottom right corner illustrates the four key parameters S11, S21, S12, and S22, showing how the VNA measures both forward and reverse transmission and reflection. In short, VNAs are indispensable tools for engineers working with high frequency components, offering broad measurement capabilities and flexibility across diverse test setups. Now, we will go into the VNA testing applications. This slide introduces the time domain reflectometric capabilities of vector network analyzer, which extends its usefulness beyond frequency domain measurements. TDR is a powerful technique used to analyze how signals behaves over a time as they travel through a transmission medium. It's especially useful for identifying faults, discontinuities, and impedance mismatches in cables, connectors, and PCB traces also. We will break down the key applications of fault location, where the TDR helps pinpoint defects in cables or connectors by identifying where reflection occurs. And impedance profiling, it allows to visualize how impedance varies along a transmission line, which is critical in high-speed digital and RF designs. And the step response shows a system reacts to a sudden change in signal, revealing transient behavior. The mathematical foundation of a TDR in a VNA is based on inverse fast-forward transform of the frequency domain as parameters. The diagram on the right illustrates a typical TDR setup using a VNA. It includes a 100 feet cable as the DUT and a 50 ohm termination and a calibrate a reference plane. The use of phase stable cable is crucial to maintain measurement accuracy. In total summary, TDR with VNA is invaluable tool for non-destructive testing and troubleshooting in applications like for the harnesses, high-speed PCBs, and RF interconnectors. Now we will go into the RF and microwave antenna testing, where this slide will give you highlights the broad utility of VNAs in antenna and passive component testing. Let's begin with the production testing. In high volume manufacturing environments, cost and efficiency are critical. VNAs offer a cost-effective solution for S-parameter testing. Components like cables, connectors, isolators, and SMF filters. Their compact form factor make them ideal for integration into automated test setup, saving both space and time. Moving to the antenna testing, VNAs are essential for measuring VSWR, voltage standing wave ratio measurements, which indicates how well an antenna is matched to its transmission line. Poor matching leads to signal reflection and power loss. With support for frequencies up to 43.5 GHz, these VNAs are well suited for testing mobile and microwave antennas, including the 5G and radar systems also. VNAs also serve as excellent replacement solutions for older, bulkier instruments. Modern VNAs are space and cost efficient, and they maintain broad testing capabilities for wide range of passive devices. Lastly, VNAs are increasingly used as a teaching tools in university labs. Their sophisticated software combined with affordable pricing makes them ideal for hands-on learning in RF and microwave engineering courses. Students can explore a real-world measurements from basic S parameters to advanced time domain analysis using the same tools found in industry. This slide outlines the key aspects of antenna testing using a vector network analyzer, specifically the ENRITSU one. Let's begin with the key parameters we evaluate during antenna testing. Return loss S11 tells us how well the antenna is matched to the transmission line. A higher return loss indicates better matching and less reflected power. And coming to the VSWR is another way to express matching. A VSWR is less than 2:1 is acceptable, typically acceptable. Bandwidth defines the frequency range over which the antenna performs effectively, and the isolation becomes important in multi-port antenna systems where we want minimal interaction between ports. This slide focused on the practical setup and applications of antenna testing using a vector network analyzer. This measurement setup is simple and powerful. VNA port 1 is connected directly to the antenna under test. This allows us to measure key parameters like S11, which represents the input reflection coefficient. On the VNA screen, you can see both the Smith chart and VSWR plot, which helps visualize impedance matching and signal reflections. Now let's look at the aircraft or antenna applications, which are using in the communications VHF and UHF radios for air to ground and air to air links. Navigation relies on antennas for GPS, ILS, which is instrument landing system, and VHF omnidirectional range. Transponders are critical for secondary surveillance radar, helping air traffic control, identifying track aircraft. Each of these systems demands high performance antennas that operates reliably across specific frequency bands and environmental conditions. Using a VNA, we can validate return loss S11 to ensure minimum signal reflection, VSWR to confirm good impedance matching, and input impedance to aid in matching network design. This setup is essential for both development and maintenance in communication systems, ensuring safety, reliability, and compliance with the standards. Now we will discuss about another testing pattern with the radiation of antennas. As we move to higher frequencies, such as used in automotive radar and 5G systems, the beam width becomes narrower and path loss increases. This makes it critical to accurately characterize antenna radiation pattern to ensure optimal performance and coverage. This is even more important in systems using multiple input, multiple output technology, whether simple or massive MIMO. In such systems, the interaction between multiple antenna elements can significantly affect overall system behavior. Here, over-the-air testing becomes essential as it offers the only practical way to evaluate real-world performance. The key measurements in radiation pattern testing include S11 magnitude and phase to assess input matching, input impedance for proper system integration, gain to evaluate how effectively the antenna radiates its energy, and pattern measurements typically performed using a positioner to rotate the antenna and capture its radiation characteristics. The measurement setups involves, as you are seeing in the slide, VNA port 1 to the antenna under test, typically placed in Encke chamber to eliminate reflection and external interface. In some configurations, port 2 may be used for pattern measurements or dual port testings. This type of testing is critical for aircraft antennas applications and navigation systems, and also weather radar systems, which typically operate in the X-band. Each of these systems has strict performance and reliability requirements, especially under extreme environmental conditions, where radiation pattern testing ensures that the antenna not only meets electrical specifications, but also radiates energy in the desired direction with the required gain and coverage. This type of testing is essential for both design, validation, and regulatory compliance, particularly in defense sectors and also in the aerospace sectors also. We will come to the filter tuning with the VNA. This slide focuses on the characterizations of RF filters using a vector network analyzer, specifically MS46122B Shockline series. Let's begin with the test configuration. This slide, the VNA port 1 connects to the input of the filter, and the output of the filter will connect to the VNA port, and this allows to measure the all 4 key S parameters in a single time. The measurements, which is S21 insertion loss or gain, will indicate how much signal passed through the filter, and S11 reflects the input return loss, which is power reflected back from input port, and S22 showing reflections at the output port, and the S12 reverse isolation, which is power transmitting backward. The key performance parameters we're looking for in a well-designed filter include insertion loss of 1 dB their passband, stop band rejection is greater than 60 dB to effectively block unwanted frequencies, and return loss greater than 15 dB in the passband, ensuring good impedance matching. In addition to electrical performance, temperature testing is also critical. Filters can drift with the temperature, so we monitor frequency drift, typically specified in ppm per degree centigrade, and VSWR stability to ensure consistent performance across the operating temperature range. There are EMI, so filter requirement applications are EMI-MC filters, IF filters, and RF filters, which will used for EMI filters are used to ensure electromagnetic compatibility, preventing unwanted emission that could interfere with other onboard systems, where IF filters are critical for receiver selectivity, helping isolate desired signals from adjacent channels, and the RF filters used for spurious rejections and filter banks, ensuring that only the intended frequency bands are passed through while suppressing the outer band of signals. Using a VNA like Enditsu, engineers can perform high precision repeatable measurements to validate filter performance during design, production, and maintain phases. Given the stringent requirements in aerospace, these filters must meet tight specifications for insertion loss, return loss, and stop band rejections. Additionally, they must maintain performance across wide temperature ranges, high variable vibration environments, and over long operational lifetimes. We'll go to the slide which will give you the explanation of how the VNA will work in the large vehicle or aircraft cable testings. In aviation, cables runs extended several meters, often weaving through complex structures. These cables are critical for connecting antennas, sensors, and communication systems, and any degradation can impact system performance or safety. There are three key parameters we focus on when testing these cables. Insertion loss measures how much signal travels throughout the cable over long distances. Even small loss can accumulate and degrade signal integrity. VSWR, which tells how well the cable is matched to the system impedance. A poor match can lead to signal reflections, reduced power transfer, and potential damage to sensitive components. And the last one is time domain analysis. This is especially useful for identifying faults or discontinuities along the cable, such as crush points or connector issues. Using the time domain reflectometer with a VNA, we can pinpoint the exact location of these faults. The image of the aircraft with overlaid cable path emphasizes the complexity and length of these installations. Testing ensures that each cable performs within specification, both during initial installation and as part of routine maintenance also. Using a VNA for this purpose provides high accuracy, repeatability, and the ability to test in both frequency and time domains. Now, we will discuss shielding effectiveness of cables in antennas. This slide compares two approaches for measuring the shielding effectiveness of cables installed with aircraft structures, a critical aspect of ensuring electromagnetic compatibility and system reliability. On the left, we see the traditional method, which involves using a benchtop two-port VNA with long coaxial cables. While this setup can deliver accurate results, but it's often cumbersome, expensive, and logistically challenging, especially when working in tight or complex aircraft environments. These long cables includes additional losses and potential measurement errors, and the equipment setup can be time consuming. On the right, we have a modern, more efficient solution using the Enritsu ME7869 system, which includes two MS46131A shockline VNAs. This setup is modular, lightweighted, and highly portable, making it ideal for inside testing within aircraft frames. The two VNAs are synchronized and connected over a control PC, which will enable accurate shielding effectiveness measurements without needing the long RF cables. This approach not simplifies the test setup, but also improves measurement accuracy by minimizing cable losses and reflections. It's a great example how distributed VNA systems are transforming field testing, making it faster and more reliable. And an advanced application of structural health monitoring, which will explain this slide. Let's start with the mobile sector. With the rollouts of 5G networks, especially in the 28 GHz and 39 GHz bands, precise return loss measurements are essential for antennas validation. The MS46131A enables high frequency testing of cables, which are increasingly used in compact and variable devices. In material measurements, the high frequency of 43.5 GHz provides superior resolution, which is crucial for detecting defects in radomes, which is nothing but radar plus dome, which will cover an antenna or protection. These measurements helps ensures structural integrity and signal transparency, especially in aerospace and defense applications. For cable inspection, the VNA supports DTF, which is distance to fall and return loss measurements. These are vital for identifying and locating faults in long or embedded cables, such as used in aircraft, satellites, and industrial systems. Lastly, the images on the right illustrate the real-world use cases, including robotic arms performing precise measurements, highlighting how this VNA integrates into automated test setups for high-frequency diagnostic. The MS46131A is a great fit for educational environments for its compact size and cost effectiveness also. Now, we will discuss about a overview of Enritsu handheld vector network analysis portfolio solutions, which are designed for field use, portability, and high performance across wide range of frequencies. Starting from the left, we have VNA Master MS20B series. The model operates from 500 kHz to 4 or 6 GHz, making it ideal for general purpose RF testing in the field. And in the center, we can see the Site Master MS2089, which covers 5 kHz to 4 or 6 GHz. This model is tailored for the low frequency applications, including land mobile radio, public safety, and IoT deployments. The SiteMaster S820E, which offers a broad frequency range from 1 MHz to up to 40 GHz, depending on the configuration. This model is particularly well suited for microwave applications such as backhaul, radar, and satellite systems. We will see little brief technical aspects here about the handheld product, which MS20B series. This is a two-port, one-path VNA that combines portability with powerful measurements capabilities and a dynamic range, which is greater than 95 dB in 10 Hz resolution bandwidth, which is low noise floor with the DANL up to -160 dB. It supports a wide range of measurements, including occupied bandwidth, channel power, ACPR, carrier to interface. Now moving to the S820 SiteMaster, this is a high performance full two-port VNA with cable antenna analyzer and vector voltmeter capabilities. It supports frequency option from 1 MHz to 40 GHz, making it suitable for both RF and microwave applications. It features a typical dynamic range of 110 dB, a full 4 receiver architecture for accurate S-parameter measurements with 1 Hz frequency resolution and 650 microsecond points measurement speed. It delivers lab-grade performance in a rugged, portable form. In summary, both instruments offer exceptional performance, portability, and flexibility, making them ideal for engineers, defense, telecom, aerospace, Navy professionals who need reliable, high-precision measurements on the go. Let me introduce the Shockline product family from Anritsu, a versatile lineup of vector network analyzers designed to meet a wide range of microwave RF testing needs. Starting with MS46522B and MS46524B, these are high-performance two-port, four-port VNAs respectively, covering frequencies from 50 kHz up to 43.5 GHz, and with E-band options extending to 92 GHz using WR12 waveguides. These are ideal for advanced applications requiring high accuracy and multi-port measurements. We have MS46121B and compact one-port USB VNAs. These are perfect for cost-effective and portable testing with frequency cover range up to 43.5 GHz. Their small form factor makes them ideal for field use or integration into test systems. The MS46322B is a two-port economical solution with flexible frequency options from 1 MHz to 35 GHz. Finally, the MS46122B is a two-port USB VNA that combines portability with performance, supporting up to 43.5 GHz. Together, these instruments provide scalable, high-performance solutions for everything from research and development to production level testing, all under the Shockline brand, known for precision, reliability, and innovation purpose. Let's take a quick look at the VectorStar VNA family from Enritsu, a premium line of vector network analyzers designed with precision, performance, and future-ready scalability. At the heart of this family is the concept of anytime upgradation, a powerful value propositions that allows users to start with a base model and scales up as their testing needs evolve. Whether you're working in R&D, production, or millimeter wave applications, VectorStar offers a tailored path forward. This lineup includes both 2-port and 4-port configurations, starting from 70 kHz to up to 70 GHz, ideal for general purpose and frequency applications. As your requirements grow, you can seamlessly upgrade to models supporting up to 110, 125 GHz, and even further 145 to 220 GHz also. This model upgrade path not only protects your investment, but also ensures you are always equipped for the next wave of innovation. In summary, the VectorStar family delivers scalability, performance, and long-term value, making it a strong strategic choice for organizations looking to stay ahead in high-frequency test and measurements. In high-frequency and precision RF measurements, accuracy is only as good as the weakest link in the setup. This slide highlights common measurements, challenges, and how to effectively address them using best practices and diagnostic tools. We begin with connector issues, often overlooked but critical. Damage, contaminations, and wear can all degrade performance. Regular inspection, proper cleaning, and tracking mating cycles are essential. Also, using the correct torque and gender adapters ensures consistent and reliable connections. Next, we face signal integrity problems. These includes noise floor limitations, dynamic range constraints, and spurious signals. Solutions involves optimizing power levels, using IF bandwidth and averaging techniques, and carefully frequency planning. Ground loops and EMI can be mitigated through proper shielding and grounding. Environmental issues also play a significant role. Temperature fluctuations, vibration, and humidity can all affect measurement stability. A controlled lab environment with isolation and shielding is key to maintaining repeatability and accuracy. Finally, Enritsu provides a suite of diagnostic tools to help engineers stay ahead of these challenges. Built-in self-test functions, versatile verification standards, Smith chart analysis, and time domain fault location capabilities empowers users to quickly identify and resolve issues. In summary, understanding these problems, areas, and applying the right solutions ensures measurement confidence and system reliability, which is exactly what Enritsu tools are designed to support. As we wrap up this overview, I want to highlight the wealth of online resources available to support your journey with Enritsu vector network analyzers. First, the Enritsu VNA product page is your central hub for all things related to VNA portfolio, whether you are looking for the detailed specifications or application notes or software updates. For those specifically working with Shockline series, we have created a dedicated Shockline VNA resource page. It offers comprehensive information on all Shockline models. Additionally, Shockline VNA collateral section includes downloadable brochures, selection guides, quick fact data sheets, and even product videos also, all designed to help you make informed decisions and get the most out of your equipment. And finally, kindly regularly check the Enritsu website for any software updates. Keeping your VNA firmware up to date current ensures your benefit from the latest features, performance enhancements, and bug fixes. These resources are curated to empower engineers and decision makers alike, making it easier to explore, evaluate, and evolve with Enritsu solutions. That brings us to the end of today's session on passive device characterizations using VNAs. I hope this presentation has provided you with some valuable insights into the challenges, tools, and techniques involved in achieving accurate measurements. When you are working at RF, microwave, or millimeter wave frequencies, the key takeaway is this: precision, repeatability, and scalability are critical. Thank you once again for your time and attention.